All right, so now we'll start by previewing the problems for our next episode, number 7. So I'll start with the first one. We have two runners, Avery and Brooks, and they're both running on an outdoor track. So Brooks is the faster runner. He completes one lap in every 78 seconds, and Avery takes 91 seconds. So the question is if, right here, Brooks passes Avery. The question is asking how long will it be until the next time that Brooks passes Avery again. So Mark was given this problem, and Mark thought that the answer was the LCM, the least common multiple, of 78 and 91. And it turns out in this case that he's correct. So our question is
his numerical
his answer, his number is correct. So our question has 3 parts. First part is to pick numbers other than 78 and 91 to prove that his reasoning of the LCM is incorrect, and that he just got lucky this time. The next part is to actually figure out what is wrong with this reasoning, beyond just showing that it gives the wrong answer. And then our third part is to modify this question slightly to make Mark's reasoning valid.
This is actually happening in my Algebra 1 class, so that's why I think it's good for people to know this. And number 2, we are talking about a heptagon, not necessarily a regular one. If it's a regular one, this probably becomes trivial. And if you have a heptagon, you can make 7-point stars by just going, say, skipping vertices around. A1 to A3 to A5 to A7 to A2 to A4 to A6 and then back to A1, right? So you have a 7-point star, and so we have 7 angles here. And we want to find out what's their sum. And then, of course, there's another way of building them. A1 goes to A4, goes to A7, goes to A3, goes to A6, and then goes to A2, A5, and then A1, right? So that also is another 7-point star. And what's the angle? What's the sum of the total vertices and angles and vertex? Okay. So this is a very natural extension of a very classical problem is about what? A pentagon, a 5-point star. What's the total? Okay.
And in number 3, we have a math contest with 100 participants. They had 3 questions. Overall, they got 200 correct answers. What we're trying to prove that there were 2 problems out of these 3 solved by at least 34 people.
These 34 people solved at least these 2 common problems, right?
So for number 4, we have given a final set of points, we have n points, and we call it set balance. If given any 2 points, there's another point that equidistant to the function set, or in other words, on their particular bisector.
So the 2 points we were talking about is any 2 points.
Any 2 points in set.
In a set. Right now it's A and B, right?
Yeah, and we can find another point in set that's equidistant from it too. And the center free basically means that given any 3 points, there does not exist a point that's equidistant to all 3. So our task is to find like some center free balanced sets. So for n equals 3, it's clear that we can just make the 3 and vertices sum equal by words. But our real task is to find equally many n, such as there exists an n-point balanced and center free sets.
All right, so now we're going to talk about the last problem on our set, which is number 5. So this is a fun puzzle problem. So after the revolution in a certain country, there's a king, and there are 65 citizens left over. And right now the king has a salary of $1, and the 65 citizens each have a salary of $1.
So after the revolution, they are all equal.
Yes.
Right?
So they're very happy. They have a perfect democracy now. Everybody is equal, and they have nominated a king. And the king has the power to propose a salary change. So what that means is he can present this plan to his people, where he describes how the salary distribution of these $66 will change among the 66 people. And he can only change people's salaries from one whole number to another whole number. So you can't go to like 0.0001 cents for somebody. It has to be whole numbers. So the key here is that when he proposes a plan,
He cannot vote.
he cannot vote.
After revolution, he's taking care of the power.
Yes. So all the people will vote instead. So the people whose salary are increased will vote yes for the plan. And the people whose salary are decreased will vote no. And the people whose salary are unchanged, they won't care and they won't vote at all. So if the number of yes votes is more than the number of no votes, then the king's plan will be passed and it will be put into action. So this
And if
king,
it's equal, I'm sorry.
yeah, if it's equal, nothing will happen. It has to be strictly more. So this king is greedy. He's also clever. So the question is, given these rules, what is the maximum salary that he can have for himself
After a few proposals.
after several proposals? So here, the number of proposals doesn't really matter. We just want to know what is the maximum salary, how does he get to that salary, and why is it maximum?
This problem is one of the many, many wonderful puzzles, math puzzles, or actually math problems from the book. What's the name of the book? Mathematical Puzzles from Peter Winkler. I learned this problem about 10 years ago by studying that book with him. And actually in his book, you can see he even tells you the background of this problem. It does have historical background from two people that he learned the problem from. Okay? And this book, the problem in a certain way is very political. They tell us democracy can only be successful with people being very alert.
Yeah.
All the things is about the people that doesn't care. Right? If you don't vote, it's very tricky. You think this thing has nothing to do with you, you never know after a few rounds, it will be very serious impact on you. Right? So let's close up our preview